In the evening of March 2nd in 1972, NASA launched Pioneer 10, the first ever mission beyond the asteroid belt. As explained by the famous NASA documentary Jupiter Odyssey, from which I got much of the footage in this video.
In early 1972, mankind launched Pioneer 10, the first mission to the outer planets, the first to venture out beyond the orbit of Mars, out through the Jupiter system, and eventually out of our solar system completely.
Before Pioneer 10, this was pretty much as good an image of Jupiter as we could get, that is, its moon Io passing in front of it, and so there was a lot of room for improvement. And here is the Pioneer 10 probe, built by TRW. The probe itself had a mass of 259 kilograms. It had 36 kilograms of hydrazine and 6 4.5 Newton thrusters, tiny little thrusters that would help keep its spin. In order to supply the 100 watts it needed to supply its instruments and its communication dish, it needed RTGs, radioisotope thermoelectric generators, bundles of plutonium that would keep it powered even as it went further and further away from the sun and solar input. It would maintain a spin rate of around 5 rotations per minute, and that rotation was kept up by its tiny little hydrazine thrusters. The launch vehicle for the Pioneer 10 was an Atlas SLV-3C with a Centaur D second stage and a Star 37E third stage. Here it is on the launch pad in Kerbal Space Program, and we will do a simulated launch here for you. As mentioned, it was a nighttime launch from Cape Canaveral, and we'll get the engine started in 5, 4, 3, 2, 1, and off it goes. You can see the original footage of the launch in the corner there. This Atlas rocket was an improved version of the one that launched the Mercury astronauts into orbit a decade earlier. It had more thrust in its booster and core stages. The booster stages were LR-89-7s, burning for 174 seconds at a maximum thrust of 1,896 kilonewtons. Its core stage was an LR-105-5, and it had a thrust of 386 kilonewtons. The added thrust meant that it could bear the mass of a much larger second stage. Remember, the Mercury astronauts didn't even have a second stage. Early on, the structure of the rocket might not even have been able to bear the mass of the second stage, but it was reinforced later on for the Agena second stage, and the second stage for this rocket is one of the most famous stages in rocketry history. It is the Centaur stage, and we will see it light up soon here as the first stage runs out. There's first stage out, decouple, and the second stage lit. Two RL-10A3s, as you can see there. The Centaur stage was the first liquid hydrogen, liquid oxygen stage in service. It was originally developed for the Saturn I rocket, but didn't see service at that point. But it has been used with some further developments ever since. It has the benefit of extremely high efficiency, but the drawback of having to keep the liquid hydrogen very, very cold, close to absolute zero, which is a technical difficulty. And of course, liquid hydrogen is also not very dense, and so you need a very large tank in order to contain all the hydrogen. So yet another drawback. But here it is, the Centaur stage, bringing the rocket to orbit and also giving the initial push towards escape velocity. And that initial push will be followed up by the extremely energetic third stage, which is the Star 37E solid booster, developing about 45 kilonewtons. It also spun up the Pioneer 10 to 30 RPM. That spin rate would be slowed down to the 4.8 RPM that it needs once the satellite becomes fully extended. Full disclosure to Kerbal Space Program fans, I had to use HyperEdit to actually get to Jupiter. I'm not currently good enough to use a solid stage rocket to hit a Jupiter transfer. In any case, here is the Pioneer 10 departing the Earth with approximately its proper spin rate. I'm not actually certain whether it was spinning clockwise or counterclockwise, but either way, here it goes. And now we have to ask the question, what was it meant to do out there once it crossed the asteroid belt and reached Jupiter? And for that, we have information from our helpful videos from the era.
The pioneers will spend 6 months to a year crossing the asteroid belt, a vast no man's land of space debris that orbits the Sun between Mars and Jupiter. The asteroid belt is 150 million miles wide. Several thousand asteroids are large enough to be assigned numbers, and some even names. An objective of the Pioneer mission is to determine the risk factor involved in traversing the belt. Mission planners believe the chance of being struck by a particle large enough to jeopardize the mission is quite low. Sizes and numbers of particles will be measured by counting penetrations of these cells. 4 telescopes will observe the brightness, speed, and direction of asteroids.
So it was Pioneer 10's job to dispel the image of the asteroid belt as this dense pack of rocks that were menacing and very difficult to navigate through. That whole image was blown away by Pioneer 10 just skirting through it. Once it got to Jupiter, it had other questions to answer.
Why a planet so large can rotate more than twice as fast as Earth, whether it has a solid surface below the seething layers of clouds, and why Jupiter radiates 3 times the energy it receives from the Sun. What causes the enormous red spot several times the diameter of Earth, and why does the dark red oval float at random with respect to the planet's motion? Temperatures, which may range from minus 200 degrees at cloud tops to thousands of degrees above zero in the interior, will be measured. A comfortable zone may exist somewhere in the atmosphere.
A comfortable zone may exist somewhere in the atmosphere. Well, I'm not too sure about that one. But there were theories about life on Jupiter, and perhaps it could be a brewing pot of the basic chemicals necessary to create organic matter. Rather than try to explain that theory myself, I think it's best to leave it up to probably the most famous proponent of that idea.
One believer is Dr. Carl Sagan of Cornell University.
Jupiter has an atmosphere rich in hydrogen and its compounds, the same kind of atmosphere that the Earth had at the time of the origin of life. So we think that the building blocks of life, at least earthly life, are being produced on Jupiter today, raining down from the skies like manna from heaven. And Jupiter may be a vast planetary laboratory in the chemistry of the origin of life that's been working for about 5 billion years. It's by no means out of the question that there are forms of life in the clouds of Jupiter. And indeed, if you viewed the solar system from afar, I think you could make an argument that life on Jupiter was more likely than life anywhere else, including on the Earth.
So we have a pretty long list of things we would like Pioneer 10 to tell us about Jupiter. And as it started its observation on July 15, 1972, when it entered the asteroid belt, and continued all the way through its closest approach of Jupiter on December 3rd, 1973, it had a great view, but the question is, how did it get that information back to us?
The Pioneers are run by men who send commands from Earth, not by automatic systems on board. This cuts complexity and costs. During encounter, it's busy here. For example, to command just the electronic camera that makes pictures of Jupiter, Pioneer Control transmits some 15,000 commands in just 2 months. Because the spacecraft is moving at up to 80,000 miles per hour, and because Jupiter is rotating at 22,000 miles per hour, the scans do not immediately form a pretty picture. They must be decoded and corrected for distortion. First, the scans are built up line by line on a television display. This gives a quick look at the operation of the system and a tantalizing hint of the spectacular pictures buried in the raw data. After the first stage of prettying up, Jupiter's first close-up portrait emerges.
So Pioneer 10 was the first to give us decent images of the giant planet, which eventually led to the much better images that we have now after subsequent probes have been sent there. But after it recorded all its information, the matter was answering the questions that the scientists had asked.
Each morning, the key scientific investigators and the key spacecraft personnel meet in the office of Pioneer Project Manager Charlie Hall for a stand-up meeting. Why not a sit-down meeting? Because, says Charlie, people don't talk so long. when their feet get tired.
I like that little tidbit, and I also like seeing James Van Allen here. He, of course, famous for the Van Allen radiation belts. No surprise that he was investigating radiation when it comes to Jupiter as well. Speaking of which, let's talk about some of the results, starting with the radiation belts, which they found wobbled around a magnetic center that was different from the center of Jupiter itself. So it was offset from the center of Jupiter. They discovered that Io had an atmosphere, and they surmised that perhaps the other large Jupiter moons might also have atmospheres. They found that Jupiter gives off twice as much heat as it gets from the Sun. They found that the white belts on Jupiter are cooler, higher clouds. They found that the day side and the night side had about the same temperature, so that was interesting. One of the major goals of Pioneer 10, though, was to assess Jupiter's gravity in order to plan for the Voyager 1 and Voyager 2 missions, which would be aiming to use Jupiter's gravity to head to the further outer planets Saturn, Uranus, and Neptune. Pioneer 10 itself, of course, was not going to head for those outer planets. Instead, it was going to slingshot around Jupiter and head into interstellar space. But along the way, it would be able to tell scientists and NASA researchers about Jupiter's gravity and therefore allow for their planning for the further missions. Of course, with Pioneer 10 being the first probe we launched into interstellar space, we wanted to, tack on some sort of message just in case somebody would spot this little object and take a look. And so here is the famous plaque that was proposed by Carl Sagan, and once again, I'll let Carl Sagan explain this plaque.
But in the remote contingency that there are interstellar spacefaring societies which might someday pick up this derelict no longer radioing, we thought we would put a message on it to indicate a little bit of where we are, when we are, and who we are. We think that the information on where we are and when we are, indicated in this part of the message by the configuration of certain cosmic objects called pulsars, will be completely obvious to any society capable of traveling between the stars. These two objects will be more mysterious because it is unlikely that there will be human beings anywhere else, even though there may be other creatures elsewhere. And the plaque has served a very useful purpose in making us think about what sort of impression we might wish to give to the cosmos.
And so Pioneer 10 headed out beyond the solar system. Its initial 155 watts at launch decayed to about 65 watts by 2005. That was not enough to supply it fully with power, and we lost contact with it on January 23rd, 2003. I think it'd be fitting at this point to hear Jupiter Odyssey, the NASA documentary's conclusion about this mission.
The domain of the outer planets is majestic beyond comprehension. The pioneers, first to brave this land of giants, first to fly forever among the lonely and endless stars of our galaxy, carry mankind's message. We're on our way.